I think YRI will really help me in the future, especially in college applications as well, because getting your research published, especially by yourself as well, with the help along mentors, and getting into national media recognition and getting into science fairs, I think YRI will help me a lot with this, because I think this will enhance my college application by a bunch due to the fact that research is there. It's going towards my career I really want to go to. Like, for example, this project was on chemical engineering and I want to be a chemical engineer. So I feel like this will keep me at a competitive edge along other competitors to get into college, and YRI will really boost this. My name is Ishaan and my project is titled Hybrid Catalytic Pyrolysis of Waste Tires using bimetal-modified zeolite and industrial waste-derived catalysts. I chose this project because tire waste is not just an engineering problem, but also a global environmental challenge that also connects to sustainability and energy. In this presentation, I'll explain the problem, my approach, the experiments and models I use, and why the results matter. Every year, the world produces over 1 billion new tires, and eventually they all become waste. These tires don't biodegrade, and traditional disposal methods are harmful. Landfills leak toxins, stockpiles catch fire, and open burning releases hazardous gases. Pyrolysis, which is heating tires in the absence of oxygen, has been studied as a promising solution. It produces three useful products: liquid fuels, syngas, and solid carbon residue. But there's also a challenge to this. Without catalysts, pyrolysis is inefficient, energy intensive, and the products are often low quality. My project explores how to make pyrolysis both more efficient and more sustainable. Researchers have tested catalysts like zeolites, which are porous materials that can crack large tire polymers into smaller hydrocarbons. Modified zeolites, especially those doped with metals like nickel or iron, increase aromatic hydrocarbon yields, which are valuable as fuels. But zeolites deactivate quickly when sulfur and carbon deposits build up. On the other hand, industrial waste materials like red mud or fly ash are cheap and environmentally friendly catalysts. They can trap sulfur and improve fuel quality, but they are less selective and not as efficient as zeolites. The gap I identified in this is very few studies have combined these two types of catalysts into a hybrid system. And almost no one has connected experimental results with predictive modeling for scale-up. That's where my project fits in. So my project used both experimental and computational methods. On the experimental side, shredded tires were pyrolyzed under controlled heating. I used advanced analytical techniques, TGIR, GC/MS, and PYGC/MS, to measure activation energies, reaction pathways, and product distributions. Differential thermal analysis and derived thermogravmetry were used to identify energy changes and mass loss events. On the computational side, I used MATLAB and Python for kinetic modeling and genetic algorithms to optimize product selectivity. Machine learning was also tested for predicting yields based on experimental datasets. Finally, I performed techno-economic and environmental feasibility assessments, because for this work in the real world, it must be cost-effective and sustainable. Now I will go to my results. The first key result is the temperature versus time graph. At the beginning, heating is slow and controlled. As the temperature absorbs heat, then the curve becomes much steeper, showing accelerated decomposition. The staged heating pattern reflects how polymers in the tire break down. With catalyst, decomposition occurred faster and more evenly, meaning the catalyst effectively lowered the activation energy and allowed conversion at lower temperatures. This is crucial for reducing energy input and increasing process efficiency. My second result is temperature versus DTA. So the DTA comes from differential thermal analysis, or as stated as DTA. The DTA curve shows that both exothermic and endothermic events at low temperatures, and the endothermic dips and appears as lighter components volatilize. Then the sharp exothermic peaks at mid to high temperatures reflect polymer cracking and aromatic formation. These peaks I noticed that these peaks were stronger and shifted to lower temperatures when catalysts were present, confirming that the hybrid catalyst promoted reactions earlier and more efficiently. Next, we'll go into the third data set, derivative thermogravimetry. So this measures the rate of mass loss. The DTG profile revealed multiple peaks, meaning the tire decomposed in distant stages. The sharpest peaks occurred at mid-high temperatures, showing the maximum rate of degradation. With the hybrid catalyst, the mass loss peaks were sharper and occurred sooner, confirming that the catalyst accelerated decomposition and improved selectivity toward liquid fuels. Next, we'll go into the discussion section. So these results suggest several key insights. That hybrid catalysts balance efficiency and sustainability. Zeolites provide high selectivity while waste-derived catalysts reduce costs and capture sulfur. Next, the system produced higher aromatic hydrocarbon yields and cleaner oils with lower sulfur content. Catalyst regeneration tests showed that performance could be maintained over multiple cycles, addressing one of the biggest barriers to industrial adaptation. Lastly, predictive modeling aligned with the experimental data, meaning the process can be scaled up more reliably. Next, we'll go into a conclusion. To conclude, waste tires are one of the most pressing environmental problems of our time. My project demonstrates that hybrid catalytic pyrolysis can turn this problem into an opportunity. By combining zeolite and industrial waste-derived catalysts, the system improves efficiency, lowers sulfur content, and increases product quality. It shows that strong potential for industrial-scale implementation and contributes to the circular economy by closing the loop between waste and energy. In short, this research shows how innovative catalyst design can transform one of the world's most stubborn waste streams into a valuable resource. I'd like to sincerely thank my mentors, especially Ishaan Jain and Dr. Subham Kumar Jalan, for their guidance. My experience with YRI was really great. So basically in school, I realized that I did a few research classes in school, like AP seminar, and currently doing AP research. So I realized in those classes that our teachers are basically our mentors, and they don't really help us as in much because there's other students as well, and they also need a help. Like at Max, they'll probably say like you need to do this, like formatting wise. But with YRI, I realized that the mentors, like Dr. Shubham, he really helps the students, especially like getting on calls with them, messaging them almost instantly, helping them figure out what they need to do, what their research is really about, and how to format things correctly and how to make it easy. I think YRI will really help me in the future, especially in college applications as well, because getting your research published, especially by yourself as well, with the help along mentors, and getting into national media recognition and getting into science fairs, I think YRI will help me a lot with this, because I think this will enhance my college application by a bunch due to the fact that research is there. It's going towards my career I really want to go to. Like for example, this project was on chemical engineering and I want to be a chemical engineer. So I feel like this will keep me at a competitive edge along other competitors to get into college, and YRI will really boost this.